Welcome to the Cosmic Pie Podcast, episode number 39. I'm your host, Wayne Barkhouse, and here with me, as usual, is
Robert Moore.
Robert. We do have a special guest today. Would you like to
Yes.
introduce our special guest?
Our special guest is our colleague, Professor Dean Smith. He works with us here at the University of North Dakota. A few of you have seen him before because he's the gentleman we usually like to come in and discuss the seasonal sky with us.
And fill in for me.
And fill in, yeah.
Robert, this 39th podcast, you haven't missed a single one. You realize that?
Oh, wow. Man, no, I haven't.
Your absenteeism is
this.
zero.
I enjoyed this. What can I say?
Were you a good student in school like that? Did you miss any
no,
day? Or
No, I miss days.
you just like this podcast? That's why you don't want to miss.
I like doing this. I really do.
Well, we really appreciate you for attending all of the episodes.
Thank you.
Especially when you're the main technical guru. If it wasn't for you, we may not be broadcasting.
We will have to fix that.
Definitely. So, Dean, thank you for joining us. How are you today?
Oh, I'm doing pretty good. Happy to be here again.
Now, Dean, looking at your background, it looks like you're in a wonderful time of the year.
Yeah, I'm
But
pretending.
But we should note there is no snow outside, right?
There isn't.
The snow that we
Yeah,
did
it all
have
melted. It's
is
actually a nice day. It's about, 50 degrees, I think?
50,
Yeah.
Got up to
So-
53 at least.
very nice.
So we got a little break from winter. It scared us, but
And I heard the end of next week we're going to get hammered again by the winter,
Right.
so it won't last. But not
And-
bad for November. I'll take it.
I absolutely, it's going to last long enough as it is. So,
Well, in case you never noticed, we are broadcasting from the campus of the University of North Dakota here in Grand Forks. If you have any questions or comments you'd like to make during the podcast, please feel free to use our chat feature. Robert over there will keep an eye on it and
yep.
let us know if anything pops up. Also, of course, the big disclaimer, our most famous disclaimer in time
Our
of
big
our
disclaimers.
podcast. Anything that Robert or I or even Dean says, and Dean can say what he wants, of course, on this issue.
especially me.
Especially you, is not necessarily the opinion of the university, nor our College of Arts and Sciences, nor the Department of Physics and Astrophysics that we're associated with, or anybody else or any other place in this whole world or universe
It's-
or whatever, or beyond.
It's just on us, folks.
Exactly. Someone say, how you can get beyond the universe? Well, there could be parallel universes out
Could
there.
be.
And that could be a subject of a podcast in the future.
Could.
See how that
We
works?
keep saying that and don't get back to many
The
of
future
them.
is still the future, Robert. It just hasn't been the present yet, you see.
Right.
Now today, to start things off, we're going to have Dean kind of do an intro on what we can see now in the winter sky, even though we hate to think about it.
Yeah.
But it's nice to be prepared, right? So,
Yeah.
Dean, fire away. What's going to happen
All
this
right.
winter?
So I actually talked about the winter sky back in episode 8. So I want everyone to go watch episode 8. And I'm done.
Okay, I'm gone.
Well,
I'm
great.
gone.
No, there's a few things. I think episode 8 was like back in, February or January or something.
Yeah.
And but we always have a little bit of different things happening. So I'm going to share
Okay.
my screen here.
And I'll go to our share screen.
So what I did back then was using Stellarium to kind of show. So Stellarium is this free software that I often recommend to people. It's planetarium software. And so this is the sky tonight. Now, one good thing about this time of year is it gets dark early. I know a lot of people complain, but I love the fact that we're back on standard time and it gets dark earlier and I don't have to wait an extra hour. So right now, if you go out, and this is set for 8 p.m. Tonight from Grand Forks. And we actually, right now, you wouldn't really get the winter if you go out early. And if you look in the west, we actually have the summer sky. We actually have the summer triangle of Deneb, Altair, and Vega. In the south, we have the fall sky. And for me, the main fall constellation I think of is Pegasus up there. So fairly high up, we got the square of Pegasus. And then we see the winter sky starting to rise in the east. And often that's kind of how things are. You'll see the previous season, setting in the west, and then you'll see the next season rising. So before I move really into the winter, which right now you do actually have to stay up a little later to see the winter stuff, things that do change over time is stuff in the solar system. So the constellations will be seasonal, and you'll see the same constellations next year. Stuff in the solar system changes, and this has not gotten a lot of news, but there's actually a comet out that you can see in binoculars. And I went out Sunday night, actually. I was not able to see it in town, but I was able to see it out of town. And it is, there it is. So it is 2023 H2. And a lot of the software is reporting it as not being very bright. So Stellarium is reporting it being almost 9th magnitude. But I think reports are that it's about 6th magnitude. So,
So
and so it is.
just to interrupt you, Dean. So do you want to explain, in case people don't know who are watching, what that difference means in terms of visibility with your eye?
Yeah, so it makes a big difference if you can see it or not. So typically with stars, we consider sixth magnitude to be the limit that you can see with your eye in a dark sky. Comets tend to be a little more difficult because they're spread out, and usually if you're going to see it naked eye, it's got to be brighter than 6th magnitude. But 6th magnitude comet, that's usually at least, you might not be able to see it with your eye, but you can see it in binoculars. So, but I did go out Sunday night, and I can, at least my report is, I couldn't not see it from Grand Forks, but outside of town, I was able to see it. And it's basically a diffuse, fuzzy thing. Not much of a tail. It's not the most exciting comet. We've had better ones. But it is a binocular comet, and it would be a small telescope comet, right? If you can see it in binoculars, any small telescope is going to give you a decent view of it. I did get not a very good picture. Well, let's see if I can find my picture. The picture was actually taken from my backyard in light pollution, and I'll just actually, am I sharing my screen or not?
You are sharing your screen.
Or am I just sharing the application? I'll share the entire screen.
Okay.
So that way I know if I drag stuff over, you can see stuff. So, all right, so I'm going to drag the picture over. And so this is a picture. This was actually just a camera on a photo tripod. This is a 135 millimeter lens for those who have cameras with lenses. And it's just on a photo tripod, so no tracking. I could only do about 2 seconds without trailing, so I took 90 pictures. And you use software to stack the pictures, and it's not too bad. 92-second exposures. And you get a little green fuzzy thing. This is about what it looked like in binoculars. Except there was no, color, to my eye. And so this thing is moving fast, and it's going to get too low to see pretty quick. And so when I saw it Sunday night, if I back up here, it was up in Aquila. And so we see in just 2 days, it's moved down and is getting into Capricorn. So it's getting lower. Good news is, it gets dark early, so you can get out. You don't have to stay up late, but you do want to get it quick. So this is at 8 p.m. But it's getting low. So by this weekend, the 17th is Friday. It's getting pretty hard to see. Yeah. So, but maybe you can go out at 7 instead of 8. So, so you do want to get out early. Look for it early. Probably use go online, look for a map. If you search for 2023 H2, you'll be able to find some star maps that show you where to look. It's not easy, right? You're not going to just look up in the sky and see it. You do need binoculars or a small telescope. So.
And at some point, the moon enters the western sky, right? In a few days.
Right. Yeah. This weekend we're going to start getting the moon, and so. So I think it's just a crescent this weekend, so it's not too bad, but it will be close. Let's let's see there we go. So Saturday on the 18th, the moon's next to it. So that's going to be,
That'll
that's going to
wash it
kind of
out.
ruin the,
Yeah.
so basically got until Friday to look for this thing. And then afterwards, the moon's going to get bigger, the comet's going to get lower. So again, it's, we've had better comets. In fact, I think the first podcast I was on when I did the winter sky, there was that green comet that the media was all excited about.
That
And
that
amazingly, this one is also green, so it's kind of weird. So,
I was
and
I was about to
so
say
we
most
haven't,
of them I've seen have been green,
yeah,
so it's
most
really not
most of
that.
them are green.
Yeah.
So, but we have another one. I think the one last January was a nicer, easier to see
Yep.
comet, but you take what you can get.
That's the luck
So,
of the Irish.
The
Yeah.
look of the Irish.
So, couple other things that we can see now are Jupiter and Saturn. Those are the main planets. Saturn, you go out early, again about 8 o'clock. Saturn's close to due south. We want planets when they're due south. That means they're the highest in the sky, and you have the best seeing. They look so. Basically, you're looking through the less atmosphere. You're going to get sharper images of the planets. So, Jupiter, this is a really good year for Jupiter. If you have a small telescope, you want to get out and look at Jupiter. And it's good because it's high in the sky. Now, unfortunately for us, planets are best in the winter. So when we're tilted away from the sun, we're tilted toward the outer planets and they appear higher in the sky. Bad news, that happens in winter. So Jupiter is a good compromise right now. Jupiter's high in the sky, but it's not freezing out, right? So we can go out and, 30, 40 degrees, it's not so bad. Jupiter right now, you do want to wait a little bit later, but about 10, 11, so not terribly late. You can get a really good view of Jupiter. It's high in the sky. Now Saturn, I have trouble viewing from town because it's low. I got trees and stuff in the way. Jupiter clears the trees. It's high in the sky by 11.
And you don't have to
And,
worry about mosquitoes, right?
You don't have to worry about mosquitoes, right? Yeah, so you can go out, 10 o'clock, get a good view of Jupiter, bring out a small telescope. Even at low power, you can see the moons. And I got someone knocking on my door.
Just
So-
just ignore it.
Come back later, please.
You're doing a famous podcast, tell them.
Right.
I'm doing a famous podcast. It is my office hours now, but I posted on announcements that my office hours start at 4 today. So
Some people can't read, Dean.
so
Yeah.
where was I? Oh, Jupiter, yeah.
Jupiter.
So low power, even binoculars, if you have them on a tripod or hold them really steady, you can see the moons of Jupiter. 50 power, you can start to see the bands, but you do usually want at least 100 power to get a good view of Jupiter. So I did go out, since I'm the special guest, I get to show my pictures. This is a picture I took Saturday night. So I was busy this weekend. We had clear skies on a weekend. So almost never happens. So Saturday night, I was able to go out and look at Jupiter, and I got a little surprised that the red spot was out. So we had the great red spot, and then the moon Io went in front of Jupiter and cast a shadow.
Nice
and
picture. Yeah.
And so it was kind of neat to get Io and the shadow. Moon shadows happen every once in a while. They're actually pretty easy to see visually in a telescope. And so the moon itself, I usually cannot see a moon in front of Jupiter. Jupiter's just so bright that it's hard to see the moon. You can get it in pictures, but the shadows just as, especially Io's shadows, just really black, dark spot on Jupiter.
Yeah.
And so this is kind of neat that you have clear sky, and you can see this sometimes. The moons will pass in front and they'll cast a shadow, and usually pretty easy to see even in a smaller telescope. The bands are usually visible. Red spot, it has to Jupiter rotate, so it's not always out. And it can be a challenge. So it's not as obvious as most people think visually in at least in a small telescope. Bigger telescopes, it's easier to see.
Can you say, Dean, a little bit more about this image? So this is not what you would see when you look through the eyepiece of your
Oh no,
telescope,
yeah,
right?
this is not what you would see. So the way I take pictures of planets is I take video, and kind of like the comet where I took 90 pictures to make one of them. You take video and then there's software that will average all the frames together. And so this video I probably had 5,000 pictures of Jupiter. Each one is terrible by itself, but you combine them all in software and then you do a lot of processing and sharpening, and you end up getting this picture. Now this is also much bigger. Jupiter's probably going to be more like this. So when you look at it in an eyepiece,
Yep.
so
Does
but-
that software, so when you take when you think, you mentioned the word seeing, so is the blurriness caused by the Earth's atmosphere, and that changes. You can think of twinkling of stars, for example, to illustrate that. So does that software allow you to take video of Jupiter, let's say, and then pick out the best seeing images and then stack those together?
right, yeah, it tries to throw out the bad ones and keep the good ones.
Okay.
Right.
And so yeah, and so I think each exposure, I for Jupiter I did like 7 milliseconds, so it's a short exposure, and it kind of freezes the scene so that the atmosphere doesn't blur it too much. But they are generally really noisy images, and so a lot of the stacking, it kind of averages things out. It also gets rid of a lot of the noise, and when you have such low noise, then you can sharpen things. So a lot of times, if you try and sharpen something, you bring out noise in the image.
Yeah.
So so averaging 5,000 pictures, you get really low noise. You can do some sharpening. So yeah, so it's able to pick up. It throws out the bad ones. I usually have it throw out like a fourth of the pictures, and keep the good ones. And yeah, it allows us to take pictures of Jupiter that are if you go back to say the 80s, this is probably better than any ground-based picture
Yes.
of Jupiter from say the 80s. So technology allows amateurs to do better than what professionals were doing before we had this technology.
So what size telescope are you using for this, Dean?
This is a 9.25-inch Schmidt-Cassegrain.
Okay.
So
So if somebody wanted to purchase, let's say, an amateur, or somebody wanted to get into amateur astronomy, what type of money are they looking at to purchase both the telescope and then the camera as well?
yeah, so I bought my telescope in 2005, so the prices have gone up, and you do want something that obviously it has to track. You are zoomed way in on something, and so you need a tracking motor to follow this thing, because when you're zoomed in at this power, it's just going to fly out of the field of view. So telescope, you're probably looking at 2,000 to 3,000. The camera I think was 250 that I used. So it's sold as a planetary camera.
Yeah.
For taking video of planets. So
My recent looks, you can probably look at about 5,000 to 7,000 nowadays for that telescope, and about 300 for the camera.
wow, okay.
Yeah.
So the
I-
cost of sending a family of four to Europe and back, you could use it to buy everything you needed then.
Right. And
Yeah.
and then spend 2 or 3 years figuring out all the processing that needs to be done.
How to use it, right?
Right.
Yeah. So yeah.
I'm sorry to disappoint some of y'all, but it does, to make pictures like this, it's going to take a good bit of doing and playing around with it and learning how to do the stacking and all that sort of thing.
Yeah. I mean, the good news, I am using all mostly free software. So there's people made software that will take these videos and do the stacking. And so I'm using one called Auto Stackert. I think it's German. So it takes a video, it lines up all the frames, stacks it, and outputs a pretty bland, low contrast image. And then you have to go and process it. And what you get changes from night to night. It depends a lot on the scene, like I mentioned, and you can go out and do the exact same thing, exact same equipment, get completely different quality pictures. And I happen to bring my one of my best pictures. This was one I took in September with the same equipment. You can see, hopefully you can see how much sharper it is. And the only difference really was the scene. And night to night, you're going to get, different scene. Even during the night, it can change.
Yeah.
And so sometimes you'll just get bad images, and there's nothing you can do about it. So this, the software can kind of try and choose the best ones, but if they're all bad,
it's bad.
There's not much you can do about it. So,
and just for information, folks, the seeing is usually determined by things like the temperature, humidity, how much the wind, how strongly the wind is blowing, and sometimes just smoke in the air, dust,
Weather fronts.
Yeah. Yeah, one time I was looking at Mars, and it was really nice, crisp, image, and then suddenly it just got all blurry and started shaking. I looked up and clouds were coming in, and in front of the clouds there's this, there's this turbulence in front of it, and it just, destroyed the image. And so,
Yep.
But that's one thing you can't control, and is a big factor on what kind of pictures you get. And when planets are low in the sky, they're usually going to be kind of blurry pictures. There's, now Jupiter's high in the sky, so every once in a while I can get a nice sharp picture. So,
Hence the reason to go to Congress and look for money to put your telescope in space.
In space, you
yeah,
don't have
this
to
is
worry about
why
the
we
air.
have space telescopes, and why the telescopes are up on mountains, right?
Yes.
You
Yep.
want to get over that atmosphere, and yeah, it makes a big difference on the resolution.
Yeah.
So,
In fact, telescopes are not put at random positions on the Earth. People actually go there with smaller portable telescopes and check what is the typical seeing you get.
Yep.
And look for places where the seeing is better than other places, and that's where you build a permanent sort of telescope, a bigger telescope.
So, yep, that's why they're where they're located, usually on mountains that are over 10,000 feet, because you're over 50% of the atmosphere at that point.
And just because it happens to be in Hawaii, that's just a coincidence.
just a nice little
Just
perk.
happened, yeah.
So, of course, once you go to the top of Mauna Kea, it's not the warm, paradise anymore.
No.
But
Going up or on your way down, it's nice.
Yes.
You could stop off when you first arrive from North Dakota or on your way back home.
Yep. So, yeah.
So, and Jupiter will be good. Jupiter basically moves one constellation every year. And it basically will be best 1 month later every year. So this year it's great in November. Next year it'll be good in December. It'll be even higher, but colder. Year after that, it'll be in January. I'm probably not going to get any pictures. So.
Oh, come on now.
That's when you go to Arizona on vacation and take your telescope with you.
I'll have to take a vacation in January. And go south, and yeah, if when Jupiter's good in January and you live further south, that's a great time to get good Jupiter images. Unfortunately, yeah, when
it's a bad time in North Dakota.
Yeah, bad time in North Dakota. So this is a sweet spot for Jupiter. It's high and nice weather. So So as far as the rest of the winter, I won't take up too much more time because we got other things. So I'll kind of bump ahead into December. where we can see more of the winter. And I talked a lot about these, back in episode 8. But I didn't cover everything. So the main constellation is Orion. I always think of that as kind of the center of the winter sky. And that usually is going to be best in December, January when it's cold. But if you stay up late, you can see it now. And oftentimes I prefer to just stay up late and look at Orion then.
Mm-hmm.
I didn't talk about last time above Orion, because there's only so much time to cover. Can't do the whole sky. So above Orion are some other constellations that I didn't talk about, and that's Auriga and Gemini. One of the main things you can see kind of in the fall and winter is the Pleiades star cluster. This is a nice binocular object that I talked about before, but there are some nice telescope clusters. So, if you've gone out and gotten a telescope and you want to, what can I look at in a telescope? The Pleiades is too big. I can only see a piece of it. There are some nice clusters in Auriga and Gemini. Auriga has M36 and M38, and let's do a little search for those. You can actually oftentimes find these. We'll zoom in. And oftentimes you can find these in binoculars. So Auriga, if you just take a pair of binoculars, you'll see these fuzzy things in Auriga. And so there's a couple nice clusters. This M36, is that one M38? Maybe I have to, yeah, there we go. There we go, M38 there. I've never heard of these names for these clusters. I always just call them by their catalog.
Yep.
So there's too many names to remember. But there's a couple nice these are open star clusters. And then down in Gemini, there's M35. There we go. And this is if you have a telescope that you move by hand. This one's actually not too hard to find. You kind of follow Gemini down, follow this arc around, and it's fairly close to the bottom star of Gemini here. This is actually a nice little open cluster. It's one of the first open clusters I think I found way back when I was looking for stuff in the sky. So Gemini and Auriga are out. Gemini is has two bright stars, Castor and Pollux, and I always remember which one is which. So Gemini is the twins, and the stars are like twins. You get them mixed up. Castor is on the side that faces Capella, and Pollux is on the side that faces Procyon. So Procyon is in this line, Canis Minor. Somehow that's a dog, and so that's how I tell those two apart. Capella is the bright star in Auriga, and from North Dakota, at least, well, from Grand Forks, Capella is actually circumpolar.
Yep.
And so even though we think of it as a winter constellation and a winter star, you can see Capella year-round. And if I go into the north, let's go into the north. We'll zoom in a little. I'll mention the North Star. I haven't really talked about the North Sky, and I've probably used up most of my time here, so I won't go into everything. But if you look for the Big Dipper, and the Big Dipper, at least here, it's always up, but it might be in different places. You take these two stars at the front of the Dipper, and you draw a line, and they go to the North Star. And the North Star is always there. It's a coincidence. It turns out as our time in history, the Earth's rotational axis points toward this star, but it's always in the same spot in the north, the same altitude. And if we put a grid on, so the grid is at north. You can see it's offset a little bit. I'm just going to animate this, and we'll watch the sky go around. And you can see the North Star stays in that spot while everything else goes around it. And so this is just going through the night. And if I turn the time on, we can kind of see we're at 2 in the morning now. So about 4 in the morning, the Big Dipper is overhead, but that North Star stays there. Everything just goes counterclockwise around it. And we keep on going. Keep an eye on this Capella here. It will skim the horizon. So this is called the circumpolar window. It's the region of the sky that never rises or sets. And so, and Capella is up year-round. There it is. It might be behind trees and buildings, but there it is due north. It does stay up year-round. So, and sometimes it's kind of annoying when I align my telescope. When I set my telescope up, I'm supposed to point it at a couple stars, and sometimes in the summer it will ask me to point to Capella. It's like, no, I'm not gonna try and find, because it's low, it's behind some tree or building or something.
Right.
So, but for whatever reason, the software really likes to align on Capella almost any time of year.
Well, it's a
So
bright star, and it's hard to mistake it for something else.
yeah, so it's a fairly bright star. So we think of it as winter, but it's out in the summer. If you got a clear horizon, you can see it skimming the horizon any time of year.
Now, Dean,
So
if you stood on the geographic North Pole of the Earth, then every star above you, other than the sun, would be circumpolar.
right,
Mhm.
and the North Star would be straight up.
Yeah.
So it would be straight overhead, and everything just rotates around it, and everything is circumpolar. Further north you go, the more circumpolar stars that you have. So,
Right.
and I got one last thing. I keep doing one more thing. This weekend, we'll go back to current time. This weekend, let's go change this to the 17th. There is a meteor shower. It's the Leonid meteor shower. And so it peaks this Friday and Saturday. It's one of the more, it's a medium shower, right? It's not like the best ones like the Perseids and the Geminids. But it's a decent shower. So most meteor showers are best after midnight because the Earth is basically traveling into the meteors. It's like, driving in the snow. It's the snow looks like it's coming at you, like you pretend you're in hyperspace. So same kind of thing. Usually meteor showers are best after midnight. Leonids especially are because all the meteors appear to come from Leo, and Leo's, well, it's not even up, right? So we have to wait until, well, we'll leave it there. There's Leo. So about, it's after midnight. So about 1 a.m. Leo finally gets up. The radiant, there we go. All the Leonid meteor showers appear to come from this spot in Leo. Now, that doesn't mean that they're all near there. They can appear in any part of the sky, but if you trace them back, they'll all appear to come from that location. So when Leo's way under the horizon, you're going to miss some of those meteors. So the Leonids are a meteor shower that's best after midnight. So you don't need anything for a meteor shower. In fact, you don't want to use binoculars or a telescope. You really want to be able to view as much of the sky as you can.
Yeah.
So
Now, Dean, did you see the article in the news? I think it was from yesterday, where there was a large brightening of a light in the sky. I think it was over in Minnesota near Bemidji area, and then a huge explosion that people heard. In fact, I seen the video from one of the ring cameras that people have, and you couldn't see the object in the sky. You could just, because it was out of the field of view, you could see the surrounding landscape light up with, and then the explosion. And people were trying to make a connection with this meteor shower with what they saw, but that seemed more like a much larger object, like a boloid type or fireball type of object that happens randomly anyways once in a while.
yeah, sometimes that just happens randomly.
Yeah,
So
and if they're large enough and you're close enough to where it's coming in, it will give you an explosion type of noise, right? So you will hear it.
Yeah, so yeah, sometimes we have those bolides come in, and yeah, they'll explode or they'll leave a big trail.
And I'll jump in here to define the term. Boloid is essentially a meteor that explodes before it touches the ground.
Right.
So
Yeah.
it explodes in airburst, if you will.
Yeah, and that definitely
Glad I had the
produces.
right term. So,
Yes, it's boloid. Yeah.
so,
But that
so
definitely produces the noise
It will
associated
produce
with
the
it.
noise because it's still in the atmosphere.
Yeah.
Yeah.
In fact, pieces of spacecraft, like you're always putting up space stuff, right? Some of that space debris coming back would act like that,
Mm-hmm.
right, and give you the same type of an effect, right?
And I've heard actually that because it breaks up as it comes in, it doesn't just pop and explode. That you can actually, if you're close to where it's going overhead, you can hear a sizzling.
Right. Yes. Yeah.
So that's kind of neat stuff.
yeah,
Yeah.
so I hadn't seen that, but yeah, they do happen every
Mhm.
once in a while.
It's just
So
that
and it doesn't
this.
have to be a meteor shower.
Yeah, because I was thinking this meteor shower, if I'm not mistaken, most of these particles are like grains of sand,
Grains of sand.
Yeah, they're
essentially.
usually pretty small.
Yeah.
So
So just a coincidence that it's within a few days of the peak of the shower, type of thing.
yeah, yeah, because sometimes these happen. There's no meteor shower,
That's right.
around at all. So I
Yeah.
mean, unless you really trace it back and get the orbit, right? Then
Yeah,
you might be able
exactly.
to link it to something.
Yeah.
So and sometimes if there's enough cameras on it, they can do that.
They can do that.
So
Triangulation is a thing.
yep. Yeah, if you get enough reports, and especially with all the ring cameras and
Right.
now you might get multiple viewpoints. So they used to have to just ask people, like,
Did you
which
see it?
direction did you see it?
Yeah.
So and it turns out eyewitness accounts aren't very good. So
Yeah.
so it's better to have the video.
Yeah.
So um so I think I'm gonna move from the sky into a news item.
Which is related to potentially to the boloids and stuff,
Yep.
right?
Yeah, so potentially related. So there is a NASA mission heading out. It's heading out to eventually to the Trojan asteroids that share Jupiter's orbit. But this one on the way is going to go past a couple asteroids in the main belt. And so it just went past this Dinkenish, I'm guessing. And it went to this asteroid. It's going to actually come back to Earth and go around the Earth and get a little gravity boost, then back out to another asteroid, and then finally back out to the Trojans. So, but this is it. Actually, they put this had it go by this asteroid kind of as a test, so they could kind of test everything out and make sure it works, before the main thing. And an interesting thing in the picture A there, they didn't know that this had a moon. So as the spacecraft was approaching the asteroid, in fact, closest approach I think was that A, it noticed it had a moon, and so that's kind of interesting, but not a huge surprise. We've actually found a lot of asteroids have moons now.
Mhm.
But then after it passed by, it looked back, and this moon, from that point of view, just looks like a normal moon. But then when it got past it and looked at it from the side, it looks like two moons. It's actually it's a contact binary, and it looks like two moons that are in contact with each other. And as far as I know, this is the first time they've seen a contact binary like this in orbit around another asteroid. So they've seen contact binaries, and they've seen asteroids with moons. They haven't seen them together like this. So this is a fairly new thing that came out, and it also leads to some interesting physics on why so many asteroids have moons and why we have these weird contact binaries. I think this is also weird because they're about the same size. A lot of times it's kind of a bigger piece and a littler piece. So this is also weird for that reason. And one of the reasons that they think these contact binaries form actually is some interesting physics. It's an effect called a YORP, YORP. Either of you heard of this effect?
I have
Yes.
not.
Yeah, this is what causes, because of the unequal heating of the surface of the asteroid, it puts out a relatively small thrust effectively off to one side. So you can
Right.
actually have the asteroid move in its orbit more than just having like an object in a certain orbit and you watch it should maintain that orbit. But it's like a small little rocket that's thrusting so the asteroid can change its orbital elements.
Okay.
Yeah, and so I know it's the YORP. They're named after 4 people. The Y is Yarkovsky, and back in the 1800s, he put forth this idea that thermal radiation would carry momentum. Before Einstein.
Wow.
Yeah, and so the Yarkovsky effect we usually think of it can the thermal radiation. You're gonna get one side's hotter than the other. As it rotates, it cools off, and you can get a thrust and change the orbit. But you can, if you have an irregularly shaped object, like most asteroids are, it's not going to have a thrust directly away from the center of mass, and you can get a torque, and the torque can spin the asteroids up. And these asteroids aren't held together very well. So there's not a lot of gravity. They're not solid rock, and there's a maximum spin rate. And so this effect can actually spin an asteroid up to the point where it can break apart. And so we think some of these contact binaries are actually asteroids that have spun up and they're starting to break apart. And eventually they could break apart into moons. And so there's a reason why this is here. So that effect can change the orbit. It can also spin them up fast enough so they break apart.
If you look in the panel A image, there's actually evidence for potentially that. That is consistent with that idea. Do you see what I'm looking at there? What's the evidence that would be consistent with that view?
Oh, there's a ridge along the center line of the little asteroid.
No, look at the moon itself.
Look at the little
little
one.
moonlet. Yeah.
You've got a ridge right
Look
through
at the
its
impact crater. There's an impact crater on that little moonlet.
Okay,
so that
yeah.
must have been part of the main asteroid when it was hit. Or it would have just busted that all to pieces, right?
Oh, yeah.
Fair point.
And then that segment of that asteroid then was separated eventually with that impact crater already on its surface.
Yeah.
You see that?
I can see that.
So that is consistent with that view.
And then that little asteroid itself started spinning so fast that it's starting to break up.
Right.
And so that's at least one model of these contact binaries is we're starting to see these things. I always thought that these were things that came in contact. And maybe some of them are, two things come in contact, but it might also be we're seeing the process of them splitting apart. So
yeah, so contact, you're thinking just if gravity was the only thing you have to worry about it, and where gravity is always an attractive force, these two bodies would move towards each other.
Yeah. And I always thought of these things as kind of maybe they're merging together, but they might actually be coming apart.
Yeah.
Right.
That seems to be the more common view now.
Well, you got to keep in mind the gravity of those things is not even the weight of a sheet of paper in your hand.
Yeah, that's very little gravity.
There's not much to make gravity stick them together.
Well, imagine you're an astronaut trying to walk on the surface of one of these things.
Yeah. Shuffling your feet puts you at escape
A
velocity.
better way of thinking about it is probably doing a EVA next to a spacecraft and maneuvering around the surface using handholds, rails, and that kind of a system rather than trying to walk on the surface of it.
Because you can't.
Yeah, there's not enough gravity to hold you down, these really small objects. So.
Yep.
Interesting. Well, there's other stuff in the news too.
Yep.
And some of these things are related to asteroids as well. And kind of the thing that came up recently has been this idea of an object, and Robert, I'll let you go into it in a lot more detail, that way back billions of years ago, about 4.5 billion years ago, roughly, that a large object impacted the Earth, and this ultimately led to the formation of the moon itself. So, Robert, do you want to bring up our slide about that and maybe describe a little bit what we're seeing here and why it's in the news today?
It's in the news today because there's these low velocity zones in the deep mantle, right above the outer core, the liquid outer core. Because keep in mind that the mantle is solid.
So you've got that little panel on the right that explains the interior structure of the Earth that you could make reference to.
So the mantle is solid. It's like a sand pile. It's a lot of little crystals that are rubbing past each other. And down deep, right up against the liquid metal core, outer core, there are these zones of rock that have lower velocity, lower wave speed from earthquake waves that pass through them. They slow down in those zones. And we've been trying to figure out for decades what these zones represented. And what they may represent is probably better shown in the next slide, where we see these nice little irregular zones, and the moon we now believe was formed because this other protoplanet hit proto-Earth. It was a glancing hit, so most of the material spun off and formed the moon, but some of it would have stuck to the Earth, the forming Earth, and sunk down towards the core. And they're now saying that may be the source of these large low-velocity provinces, or LLVPs. And that's, if it can be confirmed, would be a nice footnote on
was put up into orbit, and some of that material then ultimately collected together through gravity of its own and basically formed the moon in that case.
That's the general consensus for now.
And part of the Theia body that impacted the Earth, some of that remains as deep inside the interior of the Earth.
Right.
And that creates these asymmetries, if you like, in the distribution of density of material within the Earth itself. And that knowledge came from analyzing earthquakes.
Right. Because the density of the material it's going through determines the speed that these earthquake waves travel. And so basically what these zones are less dense regions. Well, if you think about it, the deeper in the Earth you go, you've got more stuff over you. The pressure should be higher. So the material should be getting denser, not less dense. So you've got these really strange zones where it's less dense, where the wave speed slows down.
Now, it's my understanding that one of the major constraints of the formation of the moon is when you look at the different isotopes of the minerals of the moon that were brought back, let's say, during the Apollo program and so on, that they're not exactly the same as what we have here on the Earth.
Right.
So what causes that difference?
Good question. But a lot of it has to do with the fact that the main one looked at is oxygen. And the ratio of oxygen, I think it's 15 to 16, is wrong between the Earth and the moon.
That is, it's different.
It's different. And that can happen if your two bodies that produce these, so the body that produced the moon and the body that produced the Earth, must have come from different portions of the debris disk around the forming sun. The reason is because those oxygen isotopes are different. That disk does differentiate, with heavier elements tending to fall in towards the sun more readily than lighter elements. So the heavier isotopes of oxygen should be closer into the sun, and lighter isotopes further out. The neat thing is the moon's isotopic ratio is not quite the same, but is more similar actually to Mars. And so that's why, unless I'm just losing my mind and misremembering things, so that seems to indicate and be a supporting piece of evidence that Theia came from outside of Earth's current orbit, out towards where Mars is, and spiraled in and smacked the forming Earth.
In fact, if I remember right, Theia was estimated to be roughly the mass or size of Mars.
Roughly the size of Mars, supposedly.
So that gives you an idea, how large it is.
It was just under the size needed to actually shatter the forming Earth. And add that it was a glancing blow instead of a head-on strike. And
okay, so now, so in the past, we've talked about the probability of advanced life evolving like us. That probability is, when you look at all the different things that could have gone wrong,
right,
that would have blocked the formation of evolved life forms like us, that probability is really low. That gives this whole notion of rare Earth, that book that was published, right?
Right.
About that. So now here's another thing to still continually rain into the inner solar system and bombard the Earth, so you get enough time for life to evolve to the point where it becomes like us, intelligent. But now we have to thank the Theia. the impactor, if it was too massive and hit with enough force, that would actually have split the Earth in two. We wouldn't be here to even talk about it.
There would be a second asteroid belt where Earth is.
Amazing.
It is. And, again, Theia itself would probably have done that if it would have hit more squarely.
Now, the next thing I'm thinking about, of course, is can we use seismic data, not on the Earth, but on other bodies like Mars and eventually on Venus and so on, to see if there's any asymmetries in their interior that might point to a similar formation mechanism?
Absolutely. Now, Venus, you've got to figure out a way to make the electronics last long enough.
Yeah.
But Mars, this is one of the things that we're currently screaming for, is to get a constellation, if you will, of missions to Mars so that they're all there at about the same time, because we're about to lose power to the seismograph that's on Mars because it's going into winter there, where it's located. But you really need at least 3 seismographs to pinpoint this kind of information, because with 3, you can triangulate. With 4, you can quadrilaterate and get depth as well as surface pinpointing of where things happen. And at that point, you can start telling things about how things are put together, their structure, where there's liquid, where there's solid, and things like that.
Well, another thing we've talked about is that one way to promote life on our planet was through plate tectonics.
Mm-hmm.
Would this cause plate tectonics to happen on the Earth, this type of impactor?
This is just a guess. I haven't seen any papers on that topic, but my guess is yes. Actually, it could, because if there had been a surface to the Earth already, a hardened surface, it was certainly remelted. And did it remelt smoothly, or did it remelt haphazardly and come together with joins in it?
Now, would this explain why Earth is one of the few planets that had plate tectonics? Because it was the only one that got hit by this mass ratio of the impactor versus the parent Earth at the time.
That could certainly do it. And, as we've discussed, plate tectonics they're required for getting the gas balance right on a planet, so you don't get a Venus or a Mars. You need the planets and the plate tectonics, rather, to keep recirculating the carbon for the CO2 and the nitrogen and sulfur gases and things like that. So, yeah.
Now, when we probe these asteroids, like Dean had talked about the Lucy mission, and Dean, jump in here anytime you like. One of the things we can look for is isotope differences.
Absolutely.
And that kind of, if you think of the asteroids being close to primordial or pristine material, they've been weathered at some point because of solar interaction and so on. But even if in the future, when we go to these asteroids, either by robots or human exploration, if we can get underneath the surface to get to that pristine material that's been unaltered by solar radiation,
right,
that we would have a better handle on the distribution of the different isotopes of elements from the inner solar system all the way out.
And we could start testing where the distribution of these isotopic ratios, because when you start studying isotopes, you don't look for an absolute number of a particular isotope. You look at ratios between, like, carbon 14 to carbon 12, oxygen 15 to oxygen 16. You look for these ratios because they start telling you where in the disk it was formed, because, like I said, the heavier isotopes would tend to fall in. So, a higher ratio of the heavier would say you were in closer. And, yeah, absolutely. This is why the bringing back of Comet Bennu from OSIRIS-REx and from Hayabusa, the 2 Hayabusa missions that Japan did, this is why they caused such excitement among planetary geologists, is because we were getting our hands on this material that came from these objects, and we can start testing some of these hypotheses. It's an exciting time to be getting into this type of field.
In fact, that may, if you tracked it accurately enough, these isotopic ratios, that you might be able to pinpoint fairly precisely where Theia would have came from in terms of the location.
That is one of the hopes, yes. is you can start pinpointing where that came from, where the moon, or the material that made the moon, I should say.
Yeah, because
Where
it
it
would have been on a
originated.
highly elliptical orbit that brought it to the
Right.
inner solar system if it came from outside further, right, to impact the Earth.
Right. Because people often go, well, couldn't the moon have just been captured by Earth? The answer is no. The moon is too large compared to the mass of the Earth. If it had not formed in orbit around the Earth to begin with, it would have altered its course, certainly going by Earth, but it would have kept on zooming. There's too much momentum for Earth's gravity to be able to catch something the size of the moon.
And you could show that's the case because you can run, countless simulations and changing the input parameter of your situation, the different where the moon was, a different trajectory, different paths, and see
Right.
which one of them ends up having the orbit that the moon has around the Earth today. And I would imagine that has a very low chance of happening.
Incredibly low.
So you'd have to run through millions of simulations and millions of tries before you
Right.
get success once or something.
A
Right?
success once. And so it's, as we physicists like to say, it's the 12 sigma result,
So you can't rule it out, but it's unlikely.
It's really unlikely.
Yeah, and you think the very early solar system is so chaotic, and there's so much things happening. You can't think of isolated mass particles because you're thinking about a disk of material.
Right.
So you're talking about the gravitational influence of matter that's distributed over a large length scale. Right?
And while it's low, there's gas drag still.
Right.
There's not it's really rarefied. It's more rarefied than a cirrus cloud here on the Earth's upper atmosphere. But there is still drag in the early disk. Oh, man. Yeah.
Well, and the other thing
Holy
too
cow.
is there is this notion where we find lots of solar systems now, right? Planets and debris disks, if you like, so a planetary disk around other stars.
Right.
That this whole notion of the migration of planets have come up, where planets don't stay at a fixed average distance from their host star; they can migrate inward.
Right. And they can do that due to drag created by the gas that's present or by gravitational effects.
In fact, if I remember right, even back in the mid to late 1990s, Norman Murray was leading a study, and he's at the Canadian Institute of Theoretical Astrophysics in Toronto. That the paper was based on an idea that you can actually alter the metal content, the metallicity of the host star, by having planets migrate into the star and vaporize, and that material becomes part of the outer atmosphere of the star. So if you take a spectrum of that star, then you will see more signatures of metals in that star than otherwise would be without this type of planetary migration.
And I'll point out that to an astronomer, folks, anything heavier than helium is a metal.
So oxygen is a metal.
So oxygen is a metal.
Yeah, to a chemist, they're all laughing now.
Right. The chemists are laughing, but
Well,
Yeah.
and most every other scientist.
Yeah.
Right.
Well, astronomers are simple creatures. That's what I like to
Right.
say.
So
Why complicate
there's
things?
hydrogen, there's helium, and there's contaminants. I mean metals.
And so over time, you build up the metallicity of objects,
Right.
like stars. If stars form from recycled material,
In fact, they have observed this.
Yeah.
They have observed this where a star, when we got a better spectrum of it, one that we could resolve the surface, there was blobs of higher metallicity. So it recently had eaten a planet.
yeah. In fact, I was looking at a study just a couple days ago where this group was using data from the James Webb Space Telescope to look at the abundance of oxygen in very distant high redshift galaxies, as we would say. In fact, they noticed at the very early moments, like within 300 billion years of the Big Bang, the creation of our universe, that the oxygen abundance is very, very low and quickly ramped up over the next couple hundred billion years, which is basically a signature of stellar evolution, stellar processing of that material, ultimately given rise to oxygen, through normal, blowing up of supernovae and so on.
I was about to say, says there were a lot of high mass stars living, dying, and going kabooey very quickly.
Yeah, and high mass stars, so the lifetime of a star is directly correlated with its mass. The
Right.
greater the mass, the shorter the lifetime. So very high mass stars, they only live for a few million years. We're not
Right.
talking hundreds of million, I mean literally a few
Few
million
million.
years.
Yeah.
So you can process that material quite rapidly in a few tens of millions of years. So there's not a problem with time in building up the oxygen abundance. That can happen over several hundred million years without any issue. So,
Yeah.
and it's interesting when you think about it from that point of view.
Right. It's like I had pointed out, and like I like to point out, is we can tell there was a supernova event relatively near Earth, the forming Earth, because of certain isotopes of tungsten and I think aluminum
Yeah.
that are
Fire as
present
well.
because they can only be produced in a supernova.
Right.
And they're present, or more to the point, their daughter elements are present.
Right. In fact, we implicate supernovae in the triggering of star formation.
Yep.
So our sun itself could have been formed initially because of a shock wave that propagated through this interstellar material that ultimately collapsed down to form a star, and that's
Yep.
where our sun came from.
And on that note, though, I've got to kind of bring this great discussion that I love because this is my thing, planet formation. But we need to bring it to a close. 'Cause
Well,
we're
if
at
you
4
want to
o'clock.
find out more about this kind of stuff, planetary formation, you want to learn about the impact of physics and math and chemistry,
Biology,
that.
all of it.
then take part in higher learning. Come to the University of North Dakota. You do so in person on campus, or if you can't, of course, take classes online.
Online.
In fact, Dean's with us. He even teaches an astronomy class that's online.
Yeah, you can take Physics 110, Introductory Astronomy.
Exactly. And then the other thing you can do, of course, is you can watch our podcast every week.
Absolutely.
And speaking about that, our next podcast will be on Tuesday, November the 21st at 3 p.m. Central Standard Time. And if you like this podcast, please give us a thumbs up. And the other thing is we always end with a quote.
Right?
And today's quote is from Euclid.
Okay.
So we're going way back,
Euclid.
well, back at ancient Greek time.
Right.
And the
Ancient, one of
quote
those
is-
8 dead Greek dudes.
Right. And the quote is, there are things which can be measured but cannot be articulated. So just
Ooh,
because you
that's
can measure
deep.
things doesn't mean that you really understand them. You
Right.
see?
Or more to the point, just kind of, well, we'll leave that one for another time.
That's another podcast you're thinking about,
Yep,
right?
yep. Einstein said something kind of similar. So, anyway,
So with that, thank you very much for watching, and
Thank
we'll
you for
see you
watching.
next time.